Our galaxy, the Milky Way, is an expansive collection of stars, planets, and cosmic matter that stretches approximately 100,000 light years in diameter. To put this scale in perspective, traveling from one end of our galaxy to the other would require a journey spanning thousands of years at the speed of light. Even our neighboring galaxy, Andromeda Galaxy, lie at immense distance from us. The Andromeda Galaxy is about 2.5 million light years away, making it an unimaginably distant destination for conventional spacecraft. This highlights the vastness of our universe and the challenges posed by immense distance between celestial objects. To travel in space within a short period of time, we need a potential shortcut. As you have guessed, we are going to talk about wormholes. Before delving into the wormhole theory, it's important to understand the theory of general relativity, which was formulated by Einstein. The theory of general relativity is a fundamental framework in physics proposed by Albert Einstein in 1915. It posits that gravity is not a force acting at a distance, as described by Isaac Newton's law of universal gravitation, but rather a curvature of spacetime caused by massive objects. In essence, massive objects like planets and stars cause spacetime to curve around them. This curvature creates what we perceive as gravity, a force that causes other objects to move along curved paths in the presence of this curvature. The mathematical equations of general relativity describe how mass and energy influence the curvature of spacetime. The theory also introduced the concept of gravitational waves, ripples in spacetime itself that are generated by accelerating massive objects, such as binary star systems or merging black holes. These gravitational waves were confirmed experimentally in 2015. Regarding wormholes, the theory of general relativity allows for the possibility of such structures. Within the equations of general relativity, solutions known as Einstein-Rosen bridges or wormholes emerged. These solutions indicate the theoretical existence of shortcuts in spacetime, which could potentially connect distant points, allowing for faster than light travel between them. For a simple understanding, imagine you have a piece of paper, which we call a two dimensional plane. On this paper, you have 2 points, A and B. To travel from point A to B in the shortest distance possible, you would typically draw a straight line connecting the 2 points, but it is indeed the shortest path, not a shortcut. In fact, folding the paper in a way that brings points A and B closer together could allow you to reach your destination faster. Whereas in three-dimensional plane, traveling through a shortcut could be compared to using a tunnel or a underground passage. For instance, imagine you are in a city and you want to travel from one side of a hill to the other. Instead of going over the hill, you discover a tunnel that goes straight through the hill. By using this tunnel, you can reach your destination faster because you are bypassing the obstacle that would otherwise slow you down. Just imagine bending a three-dimensional space into fourth dimension, which could potentially enable faster travel. However, it's challenging for us to envision the fourth dimension. You can grasp the concept more effectively by comparing it with two-dimensional and three-dimensional scenarios. Now, let's delve into our primary subject. In 1957, John Wheeler and his colleague Robert Fuller published a scientific article that laid the groundwork for the concept of a wormhole or an Einstein Rosen bridge. He used a metaphor involving an apple to explain it. Imagine the surface of an apple as our three dimensional universe, and the interior of the apple has higher dimensional space. If you consider poking a hole through the apple skin to its interior, you can visualize this as a shortcut or a tunnel between two distant points on the apple surface. The term wormhole became associated with these theoretical passages that could connect distant points in spacetime. Imagine spacetime has a flexible mesh where these wormholes act like openings or tunnels. They would allow for rapid travel between far flung regions, similar to using a shortcut in a network. Wormholes are typically depicted and discussed in higher dimensional spacetime rather than in just two dimensional space. The geometry is quite limited, and there is not enough room to create the kind of curvature required for a wormhole to exist. As of now, the existence of wormholes has not been proven or observed in real life. They are theoretical constructions based on the equations of general relativity, and their actual existence remains uncertain. Regarding their potential as time machines, the idea of wormholes as time machines comes from some theoretical solutions to the equations of general relativity. These solutions suggest that if a traversable wormhole were to exist, it might be possible to manipulate the geometry of the wormhole to create time loops. These could potentially allow for time travel between different points in spacetime. However, the concept of using wormholes as time machines raises numerous challenges and paradoxes, such as the famous grandfather paradox, where a person could potentially go back in time and prevent their own grandparents from meeting, leading to logical inconsistencies. Many practical problems arise here if wormholes are to be considered real. The first question is, how will the opening of the wormhole be formed? We will need an extremely heavy gravitational force here. But where can we find this gravitational force? The answer is simple, a black hole. Einstein and his assistant Nathan Rosen theorized that only black hole can have such gravitational force that they can open up these tunnels of wormholes. Everything is attracted to black holes. Everything will be attracted to it and flow through this wormhole through this tunnel. But the next question is, what will be on the other side of this tunnel? If there is a black hole on the other side, then there will be no way to get out of this tunnel. You will be trapped inside the tunnel. There should be something on the other side which is the opposite of a black hole in every sense. Something which is as powerful as black holes but works in the exact opposite way. Something that instead of attracting things towards itself, sends things away from itself so that an exit point can be created. And here enters in our story the white holes. Once again, white holes is a concept that has proven theoretically by Einstein's field equations. Apart from black holes and wormholes, white holes are another solutions of this field equation. What are these white holes? Like white is opposite to black, black holes are known for their intense gravitational pull that nothing, not even light, can escape from. White holes has would be the opposite. They would expel matter and energy outward, with nothing able to enter. This means that the white hole will be extremely bright and white in color. And the concept of white holes was first introduced by the physicist John Archibald Wheeler in collaboration with his student Robert Ruffin in 1969. And there are few theories and ideas that have been proposed regarding white holes like cosmic birth. Some theories suggest that white holes could be responsible for the origin of our universe. They propose that white holes could be the birth points of new universe, expelling matter and energy that then go on to form new galaxies, stars and planets. Hawking radiation reversal, where black holes gradually lose matter over time due to quantum effects. Some theorists have proposed that white holes could be the reverse process of black hole evaporation, where energy and matter are expelled rather than absorbed, and white holes could represent an alternative fate for black holes. Instead of collapsing to a singularity, a black hole might eventually bounce and become a white hole, releasing the energy and matter it had previously absorbed. Based on this argument, many scientists say that a white hole forms when a black hole dies. But till now, we do not have any substantial information about how a black hole dies. On the other hand, some scientists argue that there is theoretically impossible for a white hole to exist because it violates the second law of thermodynamics. As you must have studied in school, the second law of thermodynamics states that entropy in any system cannot be reduced. For example, imagine you have a room with two sections separated by a partition. On one side, you have a bunch of red marbles, and on the other side, you have a bunch of blue marbles. If you remove the partition and let the marbles mix freely, they would eventually become randomly distributed through the entire room. This mixing of colors represents an increase in disorder or entropy. The second law of thermodynamics tells us that if you were to try to separate the red and blue marbles, again you put them back into their original sections, you would need to do some work. This work would involve decreasing the entropy by reorganizing the marbles, which requires energy input. Without your intervention, the marbles would naturally mix and increase the overall disorder of the system. In the same way, black holes shred everything in the universe. Black holes swallow the entire planets and stars, and only radiation is left behind. This increases the entropy in universe. But if you try to imagine that it is happening in reverse, with the entropy decreasing, it is not possible. And if white holes do exist, then essentially this is what they will aim to do. So, as per this logic, perhaps they cannot exist. But despite this logic, some scientists believe that not only do white holes exist, but that in 2006, scientists saw a white hole. On 14 June 2006, a space satellite named Neil Gehrels Fifth Observatory captured an astronomical event. Scientists saw an explosion of white light which suddenly disappeared. This event was named GRB 060614. It was a gamma ray burst. A gamma ray burst is an extremely energetic and intense burst of gamma ray radiation. Gamma rays are the most energetic form of electromagnetic radiation, and gamma ray bursts are some of the most powerful explosions known in the universe. Usually, these events occur when a black hole swallows a big star. You can see very bright explosions of light. But in this case, no evidence of a star was found. So, it was hypothesized that it was an observation of a white hole. Since then, we have not seen such an event again. And that's why, till now, white holes is only a theoretical concept. But the thing to note here is that black holes were also theoretical at one time. But then, one day, they were practically proven. So, it's possible that in the future, the same will happen with white holes. The same thing can be said about wormholes. It's possible that they can be proven in the future. But even if their existence is proven, scientists still doubt whether humans will be able to travel through them or not. The most interesting news about wormholes' existence is from 2015 when scientists created a magnetic wormhole in a laboratory. So, till now, we were talking about wormholes in the sense of gravitational force. But if we talk about magnetic force, scientists have already been successful in creating wormholes. What does this mean? There are two ends of a magnet, a north pole and a south pole. We know that the two poles ends always stay together. Even if you break a magnet into two pieces, both the pieces will still have both poles. Scientists used some special materials and achieved something by separating the two poles of magnets and put an invisible gap between the two. Basically, the magnetic field of one magnet went inside one end of the wormhole and came out from the other end. You can see its visualization here. The left image shows a device which was created by the scientist which separates the two poles of the magnet. So, this device is basically working as a wormhole for the magnetic field. We can see this device with our eyes, but if you look at the magnetic field, in the right picture, you will see that on one side there is a pole of the magnet, and on the other side the pole is separated at a distance. Like in space, a wormhole works by bending the space-time curvature. Here, this wormhole bent the magnetic field. To make this magnetic wormhole, a high temperature superconducting material was used, known as yttrium barium copper oxide, and it was kept in a liquid nitrogen bath to conduct this experiment. Finally, friends, I would like to say that even if the existence of wormholes is not proven, in the future it doesn't mean that we cannot find other ways to travel faster than light. Theoretically, several other solutions are proposed. One is Alcubierre drive. It was proposed in 1994 by a theoretical physicist Alcubierre. This theoretical concept in physics suggests a way to achieve faster than light travel by contracting space-time in front of a spacecraft and expanding it behind. Theoretically, another solution of Einstein's field equation is presented by Alcubierre drive. It will be very interesting to see the other solutions proposed from these field equations and what practical things can be derived from them. And friends, that's all for now. If you like my video, give it a big thumbs up and subscribe to my channel. Thanks for watching.